Okay, so this evening we're going to look at L'Hopital. So L'Hopital's rule is a way of evaluating a limit when it gives you one of two indeterminate forms. Either 0 over 0 or infinity over infinity. In either case, the method is the same. The limit is equal to the limit of f prime over g prime. So you just take the derivative of the numerator, take the derivative of the denominator, and retake the limit. Now again, it's important to note that L'Hopital's rule only works if you get 0 over 0 or infinity over infinity. Any other indeterminate form does not work. And we do have other indeterminate forms that are listed. I think we went over them before, but here again. On top of the 0, 0, and 0. If you get one of the other indeterminate forms, it may be possible to rewrite what you're taking the limit of to get one of the indeterminate forms 0, 0, or infinity over infinity. And then that's what you have to do. Let's jump in.
There's one to the infinity and determinants, and then just
What's infinity?
okay, not another.
That's why.
I guess E is about 1 to about infinity. So
Limit x approaches 1, x squared minus 1 over log of x. As before, you always want to start by just trying direct substitution and see what you get. Plug in 1, what do you get?
zero.
Yay, right? That makes us happy with new stuff now. What's the derivative of the numerator? What's the derivative of the denominator?
1 over x.
What's that limit?
2.
There you go. That's what it tells you. I think it's actually pronounced L'Hopital. It's French, so it's going to have a weird pronunciation. Like L'Hopital, or something like that. I don't know. But I know it's not a hospital, that a lot of people used to call it. Because I think that a lot of the spelling is Hospital, which is not the correct spelling. It's H accent O, Pital. Plug in 0. What do you get? So L'Hopital applies. What's the derivative of the numerator?
Yeah.
What's the derivative of the denominator?
1.
What's that limit?
1.
Done.
Why is this true?
I think, proves it.
Okay.
I think. If it doesn't, then the proof is well beyond the scope of the Calc 1 course.
Okay.
But it's going to wind up using the limit definition, or the definition of a limit. Plug in 0, what do you get?
0, 0.
Again, good, that's what we want. What's the derivative of the numerator?
Cosine x minus 1.
What about the denominator? What do you get?
0 for 0.
If you get plug in 0, you get 0, 0 again, right? Read through that and see if it says you can only use it once. What's the derivative of the numerator? What about the denominator?
6.
What do you get?
0, 0.
So once again, cos x.
Cosine of x
Sorry.
is 6.
And put parentheses. Plug in 0, what do you get?
Minus 1, 6.
There's your limit.
So if the denominator has like a polynomial degree n, you have to do it like n times or something?
Not necessarily.
I mean, like in cases where it keeps being 0.
Again, not necessarily. Because there may come a point where you don't fully differentiate the denominator in terms of getting rid of x before you get a result.
Oh, you can like factor and stuff.
Right, something could happen where you'll wind up getting a result.
Okay.
Okay, now it's infinity. What do you get when you plug in infinity?
0.
Right, log of an infinitely large number is infinitely large, and square root of an infinitely large number is infinitely large. Before even doing L'Hopital's, what should this limit be? Oh dear. You should be able to tell just by looking at it.
Which one grows faster?
Yeah, which one?
That's the square root, so it goes to 0.
Yep, this limit should be 0.
0.
Let's verify it. What's the square root of the numerator?
1 over x.
What's the square root of the denominator?
1 over 2 is square root of x.
Square root of x in the denominator?
Oh.
You're saying it's 1 over the entire 2 root x? Right, it's a negative exponent. Both things should simplify to 1 over 2 root x. What do you get when you plug in infinity? I use plug here very lightly. Oh, I'm sorry. It's 2 over root x. Doesn't change anything. What do you get when you you plug in infinity.
Over infinity.
This is infinity over infinity. It's e to the negative x. Again, you should be able to see what this is going to give you, what limit you're going to get before even doing it.
0.
It's 0.
See the x grows faster.
First, let's write it as x cubed over e to the x. What's the derivative of the numerator?
20x. It's for
What about the denominator?
x e over x.
What happens? This is now this is x approaching infinity. It's technically a different theorem. Is there anyone there that says you can only do it once? No.
Wait, how's it different?
It's technically a different theorem because x is approaching infinity.
Oh, so it's the same method.
But the result winds up being the same. It says the same thing.
Okay.
Oh, I'm sorry, that's infinity over infinity case. 0 to 0. Oops. So I should have actually said that for what here. Oh, I only did that once, right? Okay, so that's the infinity over infinity case, which is technically a different theorem, but it says the same thing. So what's the derivative of the numerator?
6x.
What about the denominator?
E to the x.
What do you get?
Infinity over infinity.
What's the derivative of the numerator?
6.
Denominator.
E to the x.
What do you get?
0.
1 over infinity, 0.
Oh wait, you can like use this, like if it goes to 0 or infinity to like see which functions grow faster than other functions.
Or see if they grow at the same rate.
Can two like distinct functions?
Good. What do you get?
0 over 0.
No, 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 okay. What do you get?
0 over 0.
0 over negative infinity times 0.
That's technically undefined.
Negative infinity times 0. Make it you good? Yeah.
0 times infinity form. Bomber.
Infinity. 0.
Look, that's what doesn't imply, does it? Bomber. What do you get now?
Negative infinity infinity.
Which behaves like infinity over infinity.
Wait, but why could you do that if the law of possible doesn't apply?
Because now it does. Did I take a derivative?
No, you.
No, I just rewrote it.
Oh, I see. Okay.
I rewrote x as just 1 over x.
Okay.
Oh, but look, now it's infinity over infinity. Now L'Hopital's rule applies. Now you do it. What's the derivative of the numerator?
One of x.
What's the derivative of the denominator?
Minus x minus 2.
It's not just imply to negative x. What's that limit?
Negative 0. 0.
So what's your limit? 0. What do you get?
Zero, zero.
Derivative of the numerator.
Sine of x.
What do you get?
0, 0.
If you use direct substitution, you do. What's the limit of sine x over x?
1.
Done.
Could we have also found the rule twice?
Could have.
Okay. Oh wait, the rule was kind of like a proof for that basic limit.
You could.
Okay, I
yes.
use word proof lightly.
You could, yes. Don't know how helpful that's going to be considering you kind of need the limit definition for the derivative to prove that the derivative cosine is sine. And I think you're going to wind up with a limit that you can't take. So it's kind of weird. What do you get?
Infinity minus infinity.
Bummer. We have to rewrite this. Oh,
Yeah, wouldn't you be multiplying it by square root of x squared minus x?
plus x. It's already a minus, right? The conjugate's plus.
Oh, yeah.
Infinity over infinity.
Yeah, so the question is, I want to do L'Hopital's rule on that. What do I want to do algebra?
Divide by the highest.
Which I think is easier than L'Hopital in this case. Which is why I'm saying which one do I want to do? Well, I know which one I want to do. I want to do the algebra. Which one do I want to make you do?
You can do both.
No. I think I'll make you do the L'Hopital. So let's actually just go ahead and do it. Derivative of the numerator.
Number one,
Now for the denominator.
Something plus.
I agree, it's not plus 1.
what is it? 1/2
2x plus 1.
plus 2x.
Over.
Plus you.
That'd be 2. Plus 1. Probably the same as the numerator, right?
2x squared root x squared plus x. What now? It's infinity over infinity again.
That's more complicated than the original limit.
You don't just stick to using L'Hopital's for this.
You don't have to.
Unless
I'm not sure if one more step's going to get rid of those square roots or not.
If you split, it's like 2y over y, which simplifies to 2. Because like the square root term, I would think it blows up quicker than x. So it's done right times.
It doesn't.
Dang.
They actually increase at the same rate.
Dang.
The square root of x squared is x.
Just the plus x. No matter. If they grow at the same rate, then it's like 2x over 2x plus x. Or 2/3. If they grow at the same rate.
If I do it again, I'll get a denominator there. But then I'll get a square root there. Oh, you bastards. Yeah, L'Hopital's rules don't just keep looping forever. Because you're never going to get rid of that square root.
There is a limit, right?
Hmm?
There is a limit.
Yeah, there's a limit to 1/2. You can tell that just from that first one. Denominator acts like x plus x. You get 1 over 2x, which is a half. Or x over 2x, which is a half. So this, yeah, you're going to have to do algebra on this one.
Is that because the square root term grows at the same rate as x?
That L'Hopital's rule doesn't work.
No, I mean like that we can get the answer from, because it's like x over 2x.
Yeah, because if you let x go to infinity, x squared plus x behaves as x squared.
So we have to know which functions grow.
And the square root of x squared is x. So that denominator is behaving as x plus x. As x goes to infinity.
So it's like fine on like a test and stuff if we just point to it and say this grows at the same rate.
Unless I ask you to show algebraic justifications. Like I did on the first test. Then you have to do all the algebra. factor out the x squared from the square root, right? And you don't need the absolute value because x is going to infinity, which means all the values of x are positive. So you get half. So L'Hopital's rule, not always your best choice. Yeah, too bad you have to prove it.
That's the definition of E.
Yeah, too bad you have to prove it. How do you think we got that definition for A? We evaluated that limit without knowing it was A. If you plug in infinity, what do you get?
1 to the infinity.
No, those the same. You're just that there, right? But E is a continuous function everywhere. So the composite function theorem becomes E to the limit. We just have to examine that limit now. What do you get if you plug in infinity?
Infinity times 0.
Bummer. We're going to write that, all right? Now what do you get?
Infinity over. No, 0 over 0.
Finally, we can use L'Hopital. What is the derivative of the numerator?
One over, wait. Minus 1 over x squared times 1 plus 1 for x. Which can be simplified to minus 2
I'm not going to write it that way.
times is
I'll write it that way for right now and simplify it later. What is the derivative of the denominator?
Minus x to the minus 2.
Oh, look at that. They drop out. That's why I said I'll simplify it later. What's that limit?
1.
But is our final answer 1?
Either one.
All we did was found the exponent of a. Limit C. See that? What do you get if you plug in infinity? And again, I'm using plug in very, very loosely.
And then you get the 0 out.
That is indeterminate, and L'Hopital's does not apply. But aren't they the same? Properties of logs, right? But E is continuous everywhere. So composite function theorem. All we have to do now let's examine that limit. What do you get?
Infinity over infinity.
Yes.
But that one just goes to 0.
L'Hopital applies. This will go to 0. I don't think we've done this limit yet, have we? No, we did over square root of x. So we have to show why. What's the derivative of log x?
1 over x.
What's the derivative of x?
1. That was quick.
That limit 0. What's e to the 0? That limit's 1. What do you get? Oh wait, that is. Oh, that's typo, but I'll run with it. What do you get?
I don't know. That's like a double it. Sine of infinity. Infinity, I can't say.
What sign of infinity?
I don't know.
Yes, you do.
Yes.
Infinity? How is it 0 to the infinity?
Sign of x oscillates between -1 and +1. So you take something that's oscillating between plus and -1, raise it to a power that's ever increasing, it's still going to oscillate. So it doesn't exist. That's going to constantly oscillate. Here's what it was supposed to be. slide, let's call this 11.1. There's what the limit was supposed to be. Now what do you get?
Zero to 0. Oh no.
That is indeterminate. L'Hopital does not apply. Well, that's the same thing, right? E is continuous. So we just have to look at this limit. What do you get?
Zero times negative infinity.
Why is it negative infinity?
That's what ln does.
What if I make a minor change?
Doesn't exist.
Now it doesn't exist. So y is that negative infinity?
Data sign, the sign function on also.
It has to do something with the sign. What does sign do as you approach 0 from the right?
Go to 0.
How does it go to 0?
Positive.
From the right. All the values are positive. That's why it's negative infinity. If it was 0 from the left, sign still goes to 0. But how does it go to 0?
Negatively.
It goes to 0 from the left, and natural log doesn't exist. Which means if there's no sign there, it's just x approaches 0, that limit does not exist.
But if it's from the positive side.
From the right, it now does exist. From the left or totally, it doesn't. That's why it was important to have the 0 from the right in this problem. But that's still not proper form. Well, can't we write this? Now what do you get?
Minus infinity. You can take the minus, just
That's proper form. What is the derivative of the numerator?
it'd be cosine over sine or cotangent.
Derivative of the denominator.
Minus 1 over x squared. have 0 over 0. Positive.
So I don't want to write it that way. What happens if I use L'Hopital? I will get an answer. Because the denominator will no longer be 0. So this will definitely give me an answer. What's the derivative of the numerator though?
Two x cosine x plus minus x squared is 100. Oh, yeah, you can take out x.
Yeah, that doesn't matter. When x equals 0, numerator is 0, denominator is 1, this limit is 0. The fact that both terms in the numerator have an x makes it really nice.
Because it just
Because
times it.
both cosine and sine exist, right? They're continuous everywhere. Both of them are going to multiply by 0. Any number times 0 is 0.
I think it says like 0 over 1.
That's 0 over 1, which is 0.
Cool.
Yay! Limit exists. I'm out of room. Right there. Equals 0. So that's e to the 0, which is 1. Good? What happens?
Isn't it 0 to 0?
You want to use L'Hopital's rule?
There's like a constant 0, so you can't get the derivative of the numerator.
You can't get it at 0, but there's still a derivative function. I remember when dealing with limits, I don't care about at 0.
Maybe it's key.
But the idea comes down to the same thing. Do you really want to differentiate absolute value of x? There's a much simpler way to do it. In fact, we've done this already. We did this on the second day. No, third day. That's right. First day was just nothing. From the left, it's -1. From the right, it's +1. That limit does not exist. That's L'Hopital's rule. Questions on L'Hopital?
I'm wondering, it's like certain indeterminate forms you can make into the ones that you can use for the rule, for like algebra. Are there any forms that like, no matter what you do to them, you cannot make them compatible with the rule? 0 over 0? What is it?
I'm sure there are. question is, will you encounter them in this class? That I don't think so.
So if we encounter an indeterminate form, we can always use it.
Chances are you're gonna be able to rewrite it so it can get either 0 over 0 or infinity over infinity.
Okay.
But the question is still gonna boil down to, do you want to use L'Hopital's rule or not? What was it? This one here, for instance. It was easier to use algebra than L'Hopital. Anything else?
Is it gonna be, if we ever have Woody Cow on taxes, is it gonna be like 4 times? What did you say?
Oh, I have no idea. Could be, could not be, it depends. You have to use them multiple times. So don't forget your third project.